So welcome back after this coffee break. So now we have our second lecture of today, also by a senior fellow of BrIAS, Willem Zuidema, from the University of Amsterdam. So he will talk about language, I think much broader than LLMs. When we think about language today, it's all about LLMs, but I know that Jelle is already studying language and human language and everything related to language for also a very long time. So I'm very curious to know what you're going to talk about today and to learn more about language.
Thank you. All right. Oh, thanks everybody for coming, and thanks for BrIAS for the invitation to present here. So I put up a picture on my title slide of Nim Chimpsky and Laura N. Petito. That's from a documentary made about this great ape project, this language-trained chimpanzee in the 1970s. And I put this up for one reason, because it's a lot cuter than putting up OpenAI's $100 billion supercomputer, but also because in this talk I want to make this point that sort of like these language models, this new generation of language and speech models that we have available now, in a sense are performing the role that this language-trained apes had for science in the 1970s as a model species. And other species that we're looking at, like have they learned speech and language in a way to an extent that we can learn something about ourselves when we look at them. So that's going to be a bit of a theme. So I'm not just going to talk about large language models, but it's very closely related. I'm particularly interested in for today in transformer-based models, and so we all know that these transformer-based models are behind many of the sort of the headline-drawing developments in the generative AI field of the last couple of years. So models like the GPT models, like Claude and Llama and Mistral and Gemini, that many of us are now using on a daily basis, are actually based on the transformer architecture that was proposed in 2017. And these are all text-based models. They're trained on enormous amounts of text. But for today, I thought that it would actually be interesting to focus more on a modality that is more basic in some sense to us humans, which is the speech modality. And it's a little less known that also in the speech domain, many of the breakthroughs in the last couple of years have also sort of been based on this on transformer models. And it's not literally exactly the same setup, but we have sort of like these sort of hybrid architectures for speech, where often we have maybe a CNN layer that processes the raw input, but then it sort of like actually also goes into this sort of transformer architecture. And that's true actually also in very many other domains, in particular in image, music, and code generation domains. Now, so some of those sort of state-of-the-art speech processing models go under the names of UBERT and Whisper. And I will today mainly talk about the work that we've been doing with a model that's actually, by today's standards, from 4 or 5 years ago, already quite reasonably small. It's called the Wave2Fact2. In fact, we've been able to train one of these models ourselves on a Dutch data set of speech, and that allows for a lot of interesting analysis that you can do. So to do that, to actually feed speech to a transformer, what people do is they divide up the speech into frames, so you get this sort of continuous signal that comes in, and then you typically sample that at 50 frames per second, and then because that 50 frames per second, basically for a couple of even if it's only a minute, already gives a lot of frames. And so to make this computational bottleneck manageable, before it actually enters into this transformer architecture, it goes through this convolutional layers that sort of quantize and transform this input first. So the architecture that we'll be mainly talking about today is called Wave2Vec2. It comes out of the Facebook Meta labs so this paper from 2020. And so it starts with raw audio. That's already quite a change from the speech technology from 5, 6, 7 years ago, right? It starts with raw audio, and then we have these convolutional layers that do sort of like do this temporal convolution. So there's sort of this sliding window that goes over that input. They extract local features. Then these go into the transformer layers where these features are quantized, and the task of the transformer is to build up contextual representations, and then this model is trained on a large amount of just audio, and it's trained with something that we call mask language modeling. So basically, you can think of that that bits of pieces of the sound are covered up, and the task of the model initially is to just predict whatever you have covered, whatever you have covered, and so it's called autoregressive, self-supervised learning. So there's no labeling. It just hears all of this sort of spoken input, and then its task is to develop representations that are useful for later tasks. And then once that pre-training is finished, that's the expensive part. Then we can actually do quite cheaply supervised fine-tuning, or maybe some other unsupervised learning to make it do a particular task for us. All right. Okay. Now, based on this model and its sister models, there are others. There's LLM that comes out of Microsoft, and there's others. We've actually seen quite a revolution that is not getting as much attention as the LLM revolution, but that definitely is getting too much attention. I think we all agree on that. But it's really quite spectacular what's happening in the speech domain. So I was searching around and adapted a little for this talk this graph that shows the typical way that we measure the error, measure the performance of speech recognition systems. That's the word error rate. So if you fine-tune it then for speech recognition, so for transcribing speech into written language, and this is according to the source, the state of the art from 2012 onwards up to sort of 2022. And you see this sort of on various there's various data sets that we evaluate the performance on, this sort of really quite steep drop. In some cases, in and below the performance of humans that when they're giving the same transcription task. So we see here one of the systems, for instance, going under that 2% word error rate on particular performance. So many of you have experienced this, that suddenly when you talk to your phone and try to dictate it, this kind of software is really becoming very useful. And all of those state-of-the-art systems from the last few years are hybrid, use some technology plus a transformer somehow. So that's, for me, enough reason to focus in the rest of my talk quite a bit on that transformer architecture. Okay, great. So we have enormous progress in this particular area of AI. And there's big groups working on it. I'm actually not going to talk about how to make these models even better, how to dive even further down on this error graphs. What I'm interested in is what is happening on the inside of these models. Very much in line with the previous talk today, I'm interested in explaining what is happening on the inside. So in my group, we have, for the last 10 years, sort of dived into this problem, like how can we understand what is happening inside these deep learning models? And that turns out to be particularly difficult in the transformer age, because these transformers sort of like, it's difficult to, they've become so big, and there are so many nonlinearities and so many interacting parts that it's actually quite challenging to provide faithful and understandable explanations for what's happening on the inside. Now, maybe I just found this fascinating. So the real reason why we're doing this is that this is we find this fun. But maybe you have another idea of what is fun, and then diving into these models. So I want to reflect a little bit of like why should we even worry about opening up these black boxes? Why are we doing this? Now, one very important reason, I think, is what is now happening under the heading AI governance, right? Like, it is very difficult to actually sort of like develop regulations for this and enforce regulations for all the fancy AI applications that are being rolled out all over the world, if we don't have a better grips on what is happening, right? So these types of models for speech, but by extension also the LLM and similar technology in other domains, are deployed in real world applications all over the world, right? And at the same time, AI safety institutes and EU AI offices and all kinds of national and other regulators are rushing to sort of like find ways of sort of like of actually making sure that what these real applications are doing is actually complying with rules that we have agreed on, right? So the governments and oversight authorities, they are trying to develop regulations that ensure that these applications actually respect copyright law, privacy law, non-discrimination regulations, right to explanation, right to recourse, and not just the laws, but because sometimes these laws are still being underdeveloped, but also the ethical principles, right, on this area. So fortunately, also many companies are worried about this. Many institutions, they want to provide this. But one thing that is really important to realize is that these regulations that we are formulating, they are formulated using human understandable, almost by definition, human understandable concepts, right? So in these regulations, you find things like you are not allowed in these circumstances to do emotion recognition, right? You not recognize emotions, right? Or you're not allowed to do this and this with age or with gender, or you should sort of provide actionable feedback for the end users of this product. So we have all kinds of rules. That's really quite complicated in human understandable concepts in many different combinations, right? Now, and that means that what we need when we sort of like want to enforce this on our transformer-based generative AI revolutionary tools, we need to sort of like to have not just one concepts that we can extract from it for one particular purpose, but we actually need this sort of combinatorial layer of human understandable concepts that we can extract from this, right? So one very important motivation for the kind of work that we're trying to do of opening up these black boxes of these real-world systems is that we need to be able to check whether particular combinations of features that these things are using are actually allowed or ethical or desirable in some way. Right. Okay, this is a super important motivation for interpretability work, and I talked about this briefly at the BrIAS Responsible AI Forum organized a couple of weeks ago in this very room, and you can find that on YouTube, that entire forum. But I'm not going to actually talk much about it anymore today, because there's also a very other important reason to want to know what's happening on the inside, which is that we want to know what is happening on the inside of every complex system that exists, right? It's just the scientific, it's just the science for the science is already enough reason, I think, to open up. We have these really interesting systems. We want to know what's happening on the inside, right? So I think it's just, that might actually be the easy reason to, we just want to know, and that's what we ought to do as scientists, figure out what's happening on the inside. And in particular, if we want to use, as many people in my, people I've been interacting with over my career want, they want these kind of models to speak back to cognitive science and neuroscience. If we want to learn something from these models about how language and speech work, right? But we can only do that if we have a better grip on what is happening on the inside, right? So we want to turn these models into sort of cute little monkeys, but in order for them to be useful monkeys or apes for us, there's a couple of requirements. So these models need to be behavioral adequate. They should actually sort of be able to process language and speech in an adequate manner. They should generalize to unseen words and combinations. Now, there's now a lot of evidence that is the case. And what I'm going to focus on in the rest of my talk mainly is like, can we discover what is happening on the inside of these models if we try really, really hard, and if we take a lot of inspiration from the way we have been doing this for decades in cognitive science when we studied another black box, namely the human brain. Okay, so that was a longish introduction but in the remainder of my time, I want to actually focus on two case studies that we published in the last year, where we actually showed ways in which you can find evidence for structural rules, as I called them, inside these sort of WAF2 FAC2 style models. And one of the things I want to illustrate is that there's not one explanation technique that just works and does all the work for us. It actually requires, just as all empirical sciences, a combination of tricks and insights and intuitions, and there's a whole toolbox now of explainable AI techniques that we can shoot at this, and then we can really, also for these type of models, we can really investigate discover some really interesting features. Okay, let me move to the first case study. That this was led by Marianne de Heer-Kloots, and it's about phonetic categorization. And the starting point for our investigation is a phenomenon that everyone that has done any linguistics or phonology sort of learns in their first class, which is that human speech perception shows something that we often call categorical perception, right? So that means if I make the sound la and I make the sound ra, these have a physical realization, and if I somehow interpolate between those in some physical space, and I go in little steps from la to ra, there's actually going to be a pretty steep transition from you perceiving la to you perceiving ra, right? If L and R are in your native repertoire of speech sounds, if you speak a language where that distinction is not made, then maybe you don't hear any difference between these things. Right. Okay, but this is true for all languages of the world, all spoken languages of the world, that we seem to sort of like have this categorical transitions where either we hear this or we hear that we hear that, right? Now, but that system is not rigid, right? It is influenced by your native language. It's also influenced by the nature of the sound. So there are things like the sonority that you need to know to. But what is most important for us today is that it's also influenced by the context, right? So if we present not la and ra to you, but I present to you something like tsla and shra, right? That is already a little bit difficult for me to say because tsla is actually difficult in English because that is actually not a a permissible consonant combination, right? And sla is sla. So I can say slither, but I cannot really say slither, right? Okay. Now, it turns out that the permissibility of particular consonant combinations, what we call in linguistics phonotactic permissibility, is for humans really important. So if we go from tl to sl, from non-permissible to permissible, that boundary where we perceive an L rather than an R will shift towards the side where it's more permissible. So the boundary will shift towards the side where it's less permissible, meaning you will more quickly make the jump, right? If you go from one to the other. Like so, the gray line was the original transition, but if we're in an inabysmal to admissible context, we shift sooner to hearing the more permissible sound there. Okay, that's the basics from what we know from phonology and phonetics. Now the question we had is like, if we now take one of those state-of-the-art deep learning models for speech, can we actually show that they do something similar, and can we figure out, are they just engineering tools that just whatever you give them, they'll do something with it? Or have they actually learned from all their training data to sort of do something that reflects similar biases as humans do? So we made a whole study of trying to sort of like do experiment with wave-to-fact 2 as if it is a human, like a subject that you can do experiments with, as if it's a language-trained ape, so to speak. So we made a continuum, so that sounds like this.
La, 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 ra, 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 ra.
So at some point you might have heard a transition, and then so this is just one of them, and we make this kind of continua for all kinds of different setups, including the cases where we go from permissible to unpermissible context, and then we feed this kind of sounds into our wave-to-fact 2 model, and we can actually use something that's called the transcription head in that model to actually sort of turn sort of the inputs that we've given it into sort of like an output. So it actually says there is an L here or there is an R here. We can read that off from the final, what's called the softmax layer in that transcription head. And if we do this with the raw context, we see that like humans, the model has this sort of very categorical behavior that it gives us a sort of a peak for the L and in the first couple of steps in our in that transition, and it gives us a peak for the R so it thinks it hears raw from the fourth step onwards in that on that continuum, right? So the basic categorical perception phenomena that we know from humans can actually be repeated in a model like this. Okay, now the peak is in a particular part of the at a particular moment in time. So we're going to focus in particular at that time interval when the L and the R are in the stimulus, and then we're just going to summarize the measurements that we have here in a single graph, where we basically look at what are the peaks of the L, what is the probability that is being assigned to L versus the probability that is assigned to R, and then we get this sort of nice graphs where you see sort of the L drop and the R go up, and then there's a point where we can locate the transition very clearly there. So we can also put on top of this model what's called a little forced choice thing. So we just take the phone with the highest probability, and then that graph looks that. So I'm going to use those representations in a little bit also for the more complicated experiments that we'll be doing. So first question is, do we get human-like influences from the context on the model's decision? So we're going to sort of repeat this experiment that we know from the human literature very well, and we're going to see like how does our AI model respond to that kind of thing. And what we find is that the model is indeed also showing what we call then phonotactic sensitivity. So if we go from fle to fre, what this is our baseline, then we just repeat again what I just showed. So this is sort of the basic effect. Then when we have the tle to tre continuum here, then we actually get the you see that the transition is moving to the left towards the, so we're moving away from the inadmissible sooner. When we do it with sl to shre, then we see that it actually is moving a little bit in the other direction, right? So here are the curves on top of each other, and so you see that there's a very similar to what we find in humans, this categorical perception that is sensitive to the phonotactic context in these models. Okay, now that we have that basic thing, setup all worked out, now we can actually ask, where in the model is this actually happening? Right? So we want to dive into the model internals to sort of like see like when is this happening, and then we need a slightly different setup. So the way we're going to do this is we're gonna give the stimulus with an R to the model, or and then some or with an L to the model, or some reference stimulus to the model, and we can actually look at on all the layers of our deep learning model, and we can record like what are the activation patterns in these different layers, what do they look like, and now we're going to actually measure. So we're going to give the model a very clear stimulus with an R and a very clear stimulus with an L as reference stimuli, and then we're just simply going to measure like what do these internal states, what's the distance between the internal states that we measure in our new stimulus? Is it more similar to the L or is it more similar to the R? And we end up with this sort of this little equation where we take the distance to L divided by the distances to the two alternatives as our measure of what at this stage in the model the model thinks it has heard, right? Okay, now this allows us to not just look at the final layer, which we did so far, but also to go to earlier layers, and basically for all layers of this model, sort of try to make a map like where is this knowledge of phonotactics actually encoded in the model. And then so here we repeat with this new measure the same thing for the tle and the tr and the sl and the shre again, and we see that now the curves look a little bit more jacky, but it's basically the same thing that we had before, and then in fact if we summarize it in this forced choice setup, we get the exact same graph that we already had, and this is now for layer. This is what we had before, and then this is what if we now take the two green curves and we put them into a single graph, then we can actually sort of like build up a profile for what the different layers are doing. And basically what we're using as a measure is like the difference between the two green curves. So basically you can think of that as the moment that you want to hear, that you rather hear an R than an L, in the case when the R is actually the preferred option, or in the case when the L is actually the preferred option, and that basically that space between the two curves is now a measure for sort of like how phonotactically sensitive this particular layer is. Right? So we can do that for layer 12, and then we can also do it for other layers. So here we have I've just shown layer the convolutional neural net layer. And then you see that that phonotactic sensitivity is there in the final layer, but it's not there in the early layers. So somewhere in the transformer, this phonotactic sensitivity is building up. All right, and that blue curve there is then finally, that's actually just measuring the amount of space between the two curves. Okay, and now we can roll this out over the entire architecture. Right, and really see sort of like over the depth of the transformer of the wave-to-vec architecture, we can see this phenomenon that we're now so interested in, and we're diving so deep into of phonotactic sensitivity. We can see that emerge. You see that in the CNN, it's not there. In the input embeddings, it's not there. In layer 1, 2, 3. It's not really there, and only from layer 4, 5, 6 onwards do we see sort of that syntactic sensitivity emerging in the model. Right. Okay. Now I've asked you to come along with me on a journey of diving deep into one phenomena of speech perception, but I think it shows that you can actually take a lot of inspiration from the kind of experiments that phoneticians have been doing to understand how humans process this, to actually sort of get into quite a lot of details to figure out like where particular mechanisms in the wave-to-vec model are located. Okay, so these are just the intermediate conclusions for the case study 1. We can observe and localize sensitivity to phonotactic constraints in speech-sound configuration by wave-to-vec 2. And we can do that, I didn't really go into that, with inversions of the model that are only trained through unsupervised learning, right? So that fine-tuning for transcription step is not needed for this phenomenon to be exhibited by this model. And we can make use of classical experimental paradigms from experimental linguistics and the controlled stimulus designs that these people have already decades of experience with, to analyze the linguistic knowledge that is in these neural speech models. All right, good. I hope you're still with me. So this was one deep dive. I'm going to ask you to actually join me on another deep dive for the second case study. It's again still on phonetics, phonology, and what the second deep dive is going to be on phonological assimilation. Okay. So here we have another interesting phenomenon. Maybe you can check with yourself if that's something that applies to you as well. But the phenomenon we're interested in is like if you say in natural speech you say something like a clean. Let's take an example. I'll ask you to stick to the examples that we're going to see. But so the famous examples are things like a clean spoon, right? It's something that you like to eat from, or a clean pan, right? So these are two things that you hopefully find in your kitchen, right? If you say that in a sort of a natural way, there's actually a difference between you pronounce the N, right? Because clean spoon, you actually say a regular N in clean. But if you say clean pan, then the labial, the fact that you need your lips to sort of like to pronounce the P properly in pan, that makes it in your motor plans, and when you're saying this, that labial are needed already spreads to the way you're going to pronounce the N. And so you can actually measure in experiments that people pronounce the N in clean pan differently and more like an M, right? So you tend to say clean pan, right? Okay, so this is a very robust finding from decades of research in linguistics. The underlying lexical form is clean, but the pronunciation is more like clean when there's another consonant following that has these labial features, whereas it doesn't show that when it doesn't have it. Okay, now and so we summarize this as what's the linguists call a place assimilation rule. The fact that the place of articulation is at the lips, that is actually spreading, is assimilated by the previous consonant. Okay, now let me go in. So psycholinguists have done experiments with this, right? And they also make a distinction between what they call a viable and an unviable context. I don't know if I should go in all the detail, but in isolation, people will always say clean, but in this context, they will use that M, and then people do this sort of you can do this kind of experiments, and you ask people to actually spot whether the word clean is pronounced, and so if people change this sound, they're a bit slower. Anyway, there's lots of experimental detail that I can't really go into, but what we have in humans is the experimental results that in the viable context, in an unviable context, people are. Let me slow down for a moment. I might actually. I might have to. I went too quick here. So actually, what I should emphasize is this distinction between viable context and unviable context. So as I told you before, when you say clean spoon, we don't do this, right? If you now experimentally make the stimuli such that the N is turned into an M, in the second case, so you actually give people clean spoon, right? You can ask people like, did you hear clean, or did you hear something weird, right? And in the case of clean spoon, people say that's weird. I noticed that there was something off here. Whereas in the case of clean pan, they are less likely to do it. And the idea is that they apply this compensation for assimilation rule, right? Okay. So here we get sort of results on how humans respond to that, and where you say if we just present them with clean, there's nothing going on. But if you present the clean in an unviable context, people sort of like don't like that, and if it's in a viable context, it's still a little bit odd, but it's more acceptable than in other contexts. Right? Okay. Now we can do that same. We can try to do this same kind of experiment with wave2vec2, right? And these were the results that we got out of wave2vec2. When it's transcribing, when we ask it to transcribe the input, and we manipulate the input such that there's a little M at the position of the N, will it sort of like compensate for that and turn it back to an N? And the thing is, it will do so quite often when it's happening in a viable context, when the assimilation rule is valid, and it will do so with a much lower frequency in the unviable context when the assimilation rule is not valid, it's not applicable, right? Okay. The reason, okay, this was the basic experiment with wave2vec2, and for the paper that was published last year in computational linguistics, we also did this in a whole lot of other state-of-the-art models. So we also looked at Whisper, at U-word, large and extra large, and we basically see that same pattern of results throughout these models. And the long and short of this is that these models seem to have learned that humans very often change the N of clean into an M when they speak casually, and that shouldn't put you off guard. And if your task is to provide a transcription of the input, you should just write an N there, and so you should compensate for assimilation, right? Okay. So the model has learned a very subtle rule that you didn't even realize existed in English, that you need to compensate for place assimilation, and it has somehow learned that, and it applies that. Right? I find that in itself already a very interesting that these models learn such subtle aspects, rules of the English language in this case. Right? Now, in the final part of my talk, I want to sort of like take this as established. That's why I was trying to rush through this bit a little bit. Like the model has learned this rule. Now that we know it and we know how to measure it, can we find that rule on the insides of the model? Can we find how a rule like that is implemented in this high-dimensional neural network with its hundreds of millions of parameters? Turns out is yes, we can, right? So we can localize where the compensation is happening, right? And the way we can, there's a whole toolbox that we can now use to sort of shoot at our model. So we can use something that we call diagnostic classifiers, or that is often called just probes. So that's basically just a classifier that tries to, like a little machine learning model that looks at the internals of the big machine learning model and tries to say, like, do we find an N here or an M here? Do we find an N here or an M here, right? And basically the way we interpret sort of like these findings, if this little probe classifier is looking at one particular layer, and it says like, hey, I see an M here, even though there was actually an M in the input, right? Then that's one piece of evidence. If we find later that in a particular layer the classifier discovers that there's an N there, then we say like, oh, then we know like at that point apparently the compensation has already happened, right? So we're going to train these little classifiers to interpret what's happening in those high-dimensional embedding spaces, and at the moment that we can decode the N from it, then we say like, hey, the compensation has happened, and we're going to search for where exactly is that happening in the model. Right. Okay. So here's the setup. We give the model the audio clean fork, right? So that's an unproblematic stimulus where we give the model an N, and it should be transcribed to an N, right? And then we train a classifier to find evidence for N-ness inside the model, right? Our diagnostic classifier or diagnostic probe. And then what we see is like very early on in the transformer layer, we are at sort of intermediate accuracy. But then we see around 4, 5, 6, suddenly we jump to sort of high accuracy, and we actually sort of like the classifiers are very sure there is an N at the relevant position in the audio, right? Now we present our problematic example or our challenging example, clean pan, right? So the audio has an M, right? But we are interested in like, is the model sort of like gonna change that into an N? And what we see is that the probability that it is an N, right, it actually starts out at 50-50, so it hasn't actually learned that much in this early layer. And then it really drops in early layers. And then we see from layer 8 onwards, suddenly the probability of N is rising, and the probability of M is actually going down, right? Okay, and then we do another control. We do clean spoon. So this is the unviable context. Here it shouldn't be thing, and then you see that it actually stays consistently low. It really is not going to change that M into an N because there's no reason why it should be. So here you see that our classifiers are finding again the layer at which this knowledge seems to be represented, right? Okay. Now this is a bit similar to what I talked to you about in my first case study, and maybe you're not satisfied with this completely yet, because I'm only telling you around which layer this is happening. Before we get to dive into even more specifically, I should admit that this is a little bit cherry-picked. The clean spoon example worked particularly well in our analysis. It was the first one we tried, and it worked really well. And then we did the good thing and tried it with other examples. So we also did reg glasses versus reg lipstick versus red. And then we did it for and then we did it for, what is it, fun game, the graphs look roughly the same, but a little bit less convincing than the clean span example. But anyway, so we're just going to focus on clean pan and use this one tiny little sort of phenomenon to sort of like to try to sort of find something in this model that is maybe much more generally relevant for the bigger picture of how can we interpret LLMs that are ruling the world in a couple of years from now. Yes, but we'll start with clean pans. Okay, so what we're going to do is, so the diagnostic classifier that we find, so for that one example, we're now going to sort of do something that is called a causal intervention to really try to uncover the real computational infrastructure that this model has built up to encode that very specific compensation rule. And so we use a technique that is called interchange interventions, where we basically need a minimal pair, as we have here, clean pen versus clean spoon. And what we're going to do is we're going to give both of these stimuli to the model. We're going to record everything that the model is doing, right? And then we're going to selectively transplant activations from one run to the other run and see if it then behaves very differently, right? So for all components of the target model, we're going to systematically exchange the internal states of that model from one run with it of the other run and measure whether the model output flips to the other value. Okay, so let me explain that once more graphically. We have we take one of our stimuli, thin leaflet, that's the unviable one, and we're gonna we actually have an audio sound of that. We put it through the CNN, we put it through the transformer, and then we're actually gonna make the model sort of produce an output, and as we know, because it's unviable, it's not gonna compensate for this, the M, and it's just gonna output thin leaflet, right? And then we do one with the other one. So we have thin packet, which is a viable context, and then we're gonna the model is actually gonna compensate, and it outputs thin packet. Okay, and then we have all of like millions and millions and millions of activation factors that are in the model, and we're gonna sort of like play this game of sort of taking one component, maybe the multi-layer perceptron of one corresponding to one head in one layer of the model, and we're going to replace that one little thing from the green run and transplant it into the blue run, right? Okay, so this is called an interchange intervention, and we're going to then check what happens, and if we then get if by this transplanting only this activation into that run and then running the forward step, we suddenly get an N there, right? We know that factor has been extremely important. That information there is fulfilling the role that we're interested in, right? And this has become a really powerful way of analyzing very, very precisely what the circuitry in these models is doing. So what we measure for every intervention, we measure an intervention effect. That's basically just the probability of N minus the probability of M. And we measure that for all components. So it's computationally very expensive to experiment to do this with 2 little sound files. Right. Okay. So we have And now what we can do is we can, throughout the entire model, we can, for all the attention heads and the MLP components, for all the layers of the model, we can measure, are there some components in that model that are really, that really show a big effect. And it turns out that we get this sort of a blue sea of non-important components for the phenomenon that we are interested in. And we get 2 red dots, right? So it's actually very localized in this model. There's these 2 points, these 2 heads, so in layer 4, head 3, and in layer 4, and the MLP, that seem to sort of really have an effect on the phenomenon that we're interested in. Right, so we can, the results that we get actually depend a little bit. There's one detail that I didn't go over. Like, do you exchange just the activations in just the 1/50th of a second, the 1 frame? That is, or that we think is most is exactly where the NM difference is happening. Do you take all the frames that belong to that one phone, right? Because an M takes a couple of milliseconds, right? Or do you do it for the entire word? And so we have a bunch of different experiments where we either do this extremely localized, or we do it for the entire word, and so. Probably brings a little bit, takes us a little bit too far to go through all of these variants, but they're all in the paper. Yeah, we just wanted to end with a diagram like this, knowing that that I can't give you all the details, but what for us was extremely gratifying when we did the experiment is that for this one tiny little phenomenon of clean pens versus clean spoons, we could lay bare the exact circuitry inside the WAF2VAC2 model that is doing this. And we know that we know basically that there is in the multi-layer perceptron of layer 4, there is a representation computed that is relevant for this task. The multi-head attention mechanism in layer 5 is getting that information, right? That's what we see here on the left, and passing it on to future layers where it then stays. So there's this a very detailed understanding we could give of sort of like how all of these little components of this sort of like previously uninterpretable transformer are conspiring, are working together to deliver this one phenomena, which is compensation for assimilation. Okay. So let me conclude on that assimilation case study. WAF2VAC2 and related models do compensate for assimilation in a phonetic sense. Causal interventions, together with our probing diagnostic probes and other interpretability tools, allow us to localize how that very specific linguistic function where it is in the network, and then we can actually identify a circuit on the model where information about the following phone is available to the multi-layer perceptron at layer 3 and 4, and that information is then retrieved with attention via head 3 layer 4 and head 2 layer 5, and then distributed over multiple frames for further processing, right? And so it turns out to be yeah, we can very surgically say like, okay, that's where this is happening, and we can switch it on or off at will. Okay, Now, I hope you liked that, maybe didn't, but then it was just one example. Let's zoom out now enormously and finish up with some general conclusions, which are I've put together in this diagram. Yes, these LLMs and these speech models are massively complicated, but it doesn't mean, but they're also massively important. And it is actually societally and scientifically extremely important that we're starting to find out what is happening on the inside. And if we work hard enough, we can actually make progress. Maybe on one case, we need to do one case study after one other case study and discover all kinds of little circuitries, but it is actually achievable to understand, to localize things that are human interpretable in these models, right? We're not there yet that we can now provide to the EU AI office like a standard recipe with which we can make sure that these models are safe and non-discriminatory, right? But the field is working hard to get to that stage. And we now have this whole toolbox of tools so it's not just feature attribution anymore, so we heard, but within the feature attribution domain, there are, as we heard in the previous talk, there are already quite a few methods on the market. But in addition to that, we also have all these tools for decoding internal states. So in this talk, I talked about diagnostic classifiers, but there are also things that we call logit lens and decoder lens that are working. When we talk about, when we have a rough idea where it is happening, we have this whole toolbox of these causal interventions to sort of like uncover particular circuitry. We have all the visualization tools from data science more generally that we can use. And then there's also a set of families of interpretability tools that we haven't used. We have that I haven't used today. But we have specifically for transformers, we have these methods called attention rollout and value zeroing that are particular techniques to sort of to map how the attention mechanism is doing its work. We've got all kinds of methods to measure similarity between methods, between models. Maybe if you have a well-chosen surrogate model that really helps you to understand your target model. And then we still have all of those attribution methods that are actually the most well-known ones. Right? On all of these things, we've actually been working with that. So we have actually papers in all of these other domains as well. But let me get to the general conclusions. Advances in deep learning have mostly removed concerns about the representational abilities and learning abilities of neural networks as useful models for all kinds of tasks, and so they are also extremely useful for the cognitive sciences. We can actually learn a lot about how language works. It looks like from these models. But the remaining worry that many cognitive scientists had is that these models are not really interpretable. But so as I tried to illustrate, advances in interpretability methods are starting to remove concerns about non-interpretability. And comparing deep learning models to brains' minds is therefore no longer just one black box meets another black box, but we actually are starting to see how we can open one of those black boxes in some detail and maybe help, that really will help us understand also human brains and minds. Linguistics and psycholinguistics with their rich experimental tradition form a gold mine, I would say, for interpretability research. And studies that are using, as I illustrated a bit today, that are using insights from cognitive science and apply them to understand what's happening in large language models and neural speech models. They have not only acquired, show that they have not only acquired representations for the building blocks of speech and language, but they have also acquired subtle rules involving multiple categories, in this case of phones and words. So they are starting to offer a fascinating and relatively transparent alternative model species. They are really becoming the great apes of our age for language research. And I think we'll see many more we will see a lot of results on how human language and speech work over the coming years that are inspired by this sort of mechanistic understanding of how the fancy AI models that we built for these domains are working. So I want to end it there, and I'll just put up some more advertisement of recent interpretability work that we've been doing, because I decided to dive into sort of two very specific case studies for today on speech, but we are doing this thing also in trying to do this in the time series domain. We've also much more, this is less cognitive sciencey, but much more AI governance or organized. We have this paper, we're proud of identifying and adapting transformer components responsible for gender bias. Right? It's like you can use that same toolbox that I've tried to illustrate also for areas where maybe the cognitive or neuroscience questions are less clear, but the societal relevance is a lot clearer. And so if you're interested, I hope you read these papers. Thank you.
Questions? Yep.
Thanks a lot for the talk. I have two questions that are more broad, let's say. The first one is you compare LLM to model species, and the way I understand it is that we use those species to understand the human brains better, let's say. So, and in your talk, then you said that we need to understand them. So I was wondering if you are using it just to which part of those two things were interesting you the most, or most of interest for you, to use LLM to understand the human brain, or how human evolve, or how human learn to speak, so to speak. And the second thing is that we see that in those fields like psycholinguistic, linguistic, and neurology, it took years to understand just a tiny bit of how it works, and you're scared that the speed of the implementation of LLM is colliding with the speed of understanding them.
Yeah. Well, let me first answer, or rather avoid a little bit that first question, which is which one do I like better? Like, so I mean, my background is very much I started doing AI out of an interest of how cognition works, how the brain works. So like I thought that computational modeling was the best way in, right, to understand that. What I'm seeing is that for interpretability work, what I think is extremely important branch now in AI, there's a lot of inspiration we can get out of the cognitive and neurosciences, and sometimes as I did in my talk today, we kind of stop there and just cross our fingers and hope that at one point it will actually feed back to cognitive science and neuroscience, like I did. But that's not just happening in this talk, that's happening in my research more generally, that there's just so much happening in AI that we continue to sort of like understand specific AI models, but we don't, we are making less progress on sort of like in working out what the consequences of what we're learning about these AI models then are for our theories of the mind and the brain. Right, and so in that sense, your two parts of your question actually fit together. I realize now, because it's true. One reason why this is happening is that we work very hard on developing interpretability methods for LSTMs, and then LSTMs were killed by transformers, and then we had to start all over again and invent interpretability methods that are specifically geared for transformers. And so yes, the developments in the AI field are going very rapidly, and yeah, it's sometimes difficult to keep up. By the time that you have figured out how a particular model is really solving this particular task, sometimes the model has already gone completely out of fashion. I hope that we as a field sort of like calm down a little bit, right? Like, and so I really don't like it when reviewers say an LSTM interpretability method cannot be published anymore because no one works on LSTMs. I mean, I think we should put the scientific concerns of like what's interesting, what is thorough, so put those first. Yeah, I hope that answers more or less your question.
So, oh, okay. I have, of course, a super interesting talk with so many things to think about. So my brain is having difficulties keeping up. So I have two questions. One very technical, one more like a remark. So in the interchange intervention paradigm, right? So you're putting in an activation or from one stream in another. But doesn't that create like an inconsistency, like something that would, like, I assuming the system is, there's no randomness in the system, so it's causal, right? So isn't that causing a problem? Like
No, but it's working. But in a sense, it's already a discovery of the field that this is that you can make sensible interchange interventions, right? And so there's two reasons why this works. One reason is that we choose stimuli here that are very similar, right? So we have thin leaflet and thin packet, so they are chosen to be we've chosen stimuli that are of equal length in measured in time, and there are also very similar word combinations, right? So that hopefully our interchange intervention really only affects the phenomenon of interest. The other reason is a feature of these transformer models, which we have realized in the last couple of years. So there's something that people call the residual stream. So I don't know, it gets a little bit technical, but around every component in a transformer, there's a residual connection that basically copies a little bit of the activation value that was there before that component to the one that is after that component. And what we now understand is that the residual stream anchors the representation throughout all of these layers in sort of a common embedding space. And therefore, these representations are somewhat modular, and therefore you can even do this. You can literally transplant the activations that you find right there from one run, and just copy it to the other. But that works. It's been a significant discovery of the field of mechanistic interpretability.
And the other thing was when you started with the clean spoon versus clean pan. I was immediately starting to write down this is work for if you do the wrong cake and the wrong pan so changing the nasal,
Yes.
because the N is kind of like a default nasal. Even if you wouldn't pronounce it, if you would just say clean pan, then
People would still get it.
Yeah, would still get it. So I was making a note. I was like, how does your? And then you were basically saying it doesn't work as well with the other nasals. It seems that what I mean, and then I was thinking, but that's exactly what you would expect from human subjects too. So I mean, it's not it doesn't seem to be a weakness of your result that you don't find that it works as well.
Okay, that's good to hear. I must admit that we kind of stopped there. We put a little footnote in, like, okay, this example is cherry picked, but I mean, but that doesn't mean that it's not that the phenomenon that we're finding is real. But it doesn't seem to be that our compensation rule is as general as the one that has been described in phonetic textbooks. But we don't even know whether that is the perfect description of what's happening in humans. So. That would be interesting to follow up on that. Thank you.
Other questions? Maybe a question is, if you would now look back at older architectures that were maybe also doing a reasonable job, would you see similar phenomena, or is it just impossible to do this kind of interventions in older models, or
Yeah.
so can we understand why they were more limited in a similar way, or?
Well, that depends a little bit on how far back you go to older architectures. So basically, like 5, 6, 7 years ago, like a lot of the speech technology was based on for instance, LSTMs, and that's there it's actually harder to do this interchange interventions because of the lack of modularity in the internal states, and that has to do with what Bart just was raising. If you go even further back, then we had a sort of proud tradition of building hand-designed hidden Markov models, and then this rule was in there again, but it was actually done by proper knowledge of how language works, and people had actually coded this sort of like as an exception rule in the systems that you need to compensate for. So I think this specific phenomenon is there. This methodology that is now available depends in some extent on some like coincidental features of transformers. So the transformers were not designed to be modular, but they ended up being somewhat modular, but only somewhat, because of particular design choices that made to make them efficiently run and parallelizable, etc. And so one thing I think, one important research area for the future, I think, is to not have interpretability as a nice afterthought after having spent your hundreds of millions on training fancy models, but to actually sort of like find models that are as performant as the transformer models of today or better, but are more transparent by design, right? And this is something, I don't know if there are any politicians in the room, but this is something I find frustrating, that sort of like this is not in, the big companies are not particularly interested in this, right? So they put all their bets on this sort of massive, bigger transformer-based models, whereas it might actually be societally very relevant to also put efforts into models that sort of that put the balance between explainability and performance a little bit more towards making them more explainable without having to give up too much on the performance that they do.
Okay. Thank you. There are no other questions. I'd like to thank Jelle again.
Thank you.